This is question 8 of the Winter 22 final exam walkthrough. Okay, so this question is about a combination of cache and virtual memory and their architecture. So the question says you've been tasked to configure the memory system for a processor for a company. The cache is virtually addressed. Virtual memory uses a single level page table, and there is no TLB. Okay, so basically we're given a system, and then it says we have access to the following technologies. So we have 2 types of caches. We have each which costs a different amount. We have 2 types of DRAMs, each which costs a different amount, and we only have 1 type of SSD. Okay, so it says, considering this system, write down the coefficients for the average memory access time. LC, LD, LS represent the latencies for the cache, DRAM, and SSD components, respectively. You can assume that any necessary updates to cache, page table, and DRAM due to cache miss or page fault would happen in parallel to data retrieval. Okay, so basically it gives us a nice diagram here, which I really like. But it says compute the AMAT, or make a general equation for the AMAT. So we don't actually need this table at all for this part. This is just kind of a purely conceptual thing. So basically we need to determine alpha, beta, and gamma. Is that what it is? Yeah, I don't know Greek letters. I should. But okay, so that's lambda, isn't it? Yeah, whatever.
Yeah, it is gamma, I think.
Is it gamma or is it lambda? I get
lambda.
switched
Lambda's
up.
the
Is
one
lambda the
that's
upside?
flipped.
Lambda's
Yes,
that, right? Yeah.
Lambda's the other way.
Okay. So alpha is the basically something times the latency of the cache. In other words, we're trying to determine for every time I do a virtual address access, what proportion of times do I need to access the cache? Well, as you can see from the diagram here, 100% of the time, right? Every time I do a virtual address access, I access the cache, right? And I never access the cache twice, right? So that tells me that alpha is just equal to 1, right? 100% of the time, I'm going to access the cache. So then beta represents how many times, or like per, on average, how many times am I going to access the disk? Well, in this diagram, there's only 2 times I access the disk. I access the disk if I do a page table walk, right? Because my page tables are inside my disk. Or no, wait. Yeah, are inside my disk. I think it said that at the start. And my DRAM, right? Or not disk. I don't know why I was saying disk. DRAM, right? That's what LD is. So I access DRAM if I'm doing a page table walk, or if I get a hit in my page table walk, and so I can get the value from DRAM, right? So how often does that occur? Well, it tells us here the weights of how often something occurs. So if we have a hit rate of 80% in our cache, that means 0.8 times percent of the time, or 80% of the time we're going on this arrow. That means 20% of the time we're going to have a miss, right? So that means 20% of the time we're going to have a DRAM access, right? But there's still the potential that I access DRAM again, right? Because what if I get a hit? So what percent of the time do I get a hit? Well, 90% of the time, 0.9, right? So now you might say like, this is 0.9, but that's not true. It's 20% of, or 90% of the 20% of the time, I get a hit in my page table, right? And if I get a hit in my page table, then I get, I do another DRAM access. So this 0.2 correlates to how often we are accessing the page table, right? And this, it'll be 0.18. It corresponds to how often we're accessing the DRAM. So this will be, the sum of that should be 0.38. So then our LS is our SSD or a disk, right? So how often are we accessing that? Well, we only access, let me clean this up a little bit. We only access our disk when we get a miss here. So that's a 0.1, right? And so how often do we do it? Well, it's 0.2 times 0.1, which is 0.02, which is right. So what we're doing here is we're letting these variables here represent the latencies, right, for each of these access. What we're trying to do is determine how often or like what proportion of times do we do this. So this is very similar to what we were doing back when we were computing. Well, we've done very similar AMAT calculations, but we've never just presented you a situation where we just leave the latencies as variables. So that's all that this question is. So then moving on to B, it says, well, we have a couple of restrictions. AMAT needs to be less than 25 nanoseconds, and we only have $100. Circle the ideal technologies to minimize the latency while meeting the cost budget. Okay, so it says we can choose between SRAM A and B. We can choose between DRAM 3 and 4, and we have to use that SSD. So we only have $100. So let's look at what options I can actually consider, because I don't need to consider, every single combination if there's cost constraints, right? So I have to use the SSD, and the SSD costs $20. So that means I have $80 left to choose between my cache and my DRAM, right? So let's assume that I chose the more expensive cache, right? I chose cache B. If I choose cache B, I cannot afford having DRAM 4, right? So I have to use DRAM 3. So if I use cache B, right, if I underline that, I have to use that. If I assume I use DDR4, right, then I can't afford SRAM B again, right? So I have to use SRAM A, right? So I have to use that. And in all reality, right, do I even want to consider this combination, or do I even want to consider this combination of using the cheaper ones, right? Well, the cheaper ones have lower latency or higher latencies, right? And so, like, yes, while I could afford doing that, it just seems unideal, right? So there's really no point in considering the cheap option, right? Which is, even though I could do these two together, there's really no point. So we really only have two configurations that we want to consider, and we want to determine which one minimizes the latency, right? Well, if we want to consider that, basically we're just going to plug stuff into what we determined here, right? So if we just do like AMAT for green, which is the configuration with SRAM A and DDR4, we get that our AMAT is alpha, which is 1 times the latency from the cache. So that's going to be, for green, it's going to be latency from cache is 2. So 1 times 2 plus 0.38, which is beta, times the disk latency, which is 10 nanoseconds, plus gamma times latency from SSD, which is just 800 nanoseconds. And then for the blue option, our AMAT is equal to 1 times 1, right? The one coming here, plus 0.38 times the other DDR, which is 20. And then the last part's not going to change. Right. So these are my two AMATs. So somebody want to throw those into a calculator? If not, I can.
I think the first one is 21.8.
Okay.
And the second one is
24.6.
Okay. So we can tell that this one is better. It minimizes our latency. right? And so that's our answer, right? We would circle this and this. Okay, so then in part C, it says, using the equation in part A, what would the AMAT and total cost be for the technologies selected in part B? So the AMAT we determined was 21.8. The cost, well, so our SSD is 20 bucks. Our SRAM, we chose the cheaper option. So we went with 20. And then our DRAM, we went with 45. So it'll be 20 plus 45 plus 20, which is 85. Awesome. Any questions on this question?
Can we go over A real quick?
Yeah.
So my biggest problem is that they have like this magical equation in the like solutions where it's like 1 plus 0.9 times LD plus 0.2 or something times LD times LH, and then it becomes like a like an algebra problem where you combine all like terms and whatever, but like that equation isn't general. Like that's not something like I wasn't able to get that because I thought about it from like the perspective of like one of the homework problems, which is a little different. But like this, they're just like, assume that they're like variables that add up to something like that. So I guess my question in regards to, or is sort of how am I supposed to come up with an equation on the fly like this? Because I can't really do a math problem. So I always fail them these things.
So yeah, let me pull up the solutions real quick. I haven't seen one in a while. Actually, I think I know what you're talking about.
I think they're just using conditional expected value for the problem because they're just saying, oh, like given that we already know it's in the 20% that we miss or something, like you'll have you'll have to do some others, you have to do all this extra work is basically what they're saying. They're like using conditional expected value. I think like you don't really need it. You can just determine like all the intersections like how Sunny did. And I think it should be working exactly the same.
Yeah, okay. So I'm looking at what they did. Yeah, so I think that pretty much captures it, right? So there's a bunch of ways to work about this question. I see the way that they solved it, right, is they made their generalized equation, right? Which is we usually do with like the numbers in class, right? But I think my approach just makes more intuitive sense because just kind of logic about like where like logic about each of these variables being the proportion of times that we're accessing something, right? I think that makes a lot more sense, and generalizing in that form instead of just kind of memorizing a formulaic way of doing it is probably a better way to go about it. I understand why you weren't able to create that formulaic representation because honestly, I wouldn't have approached that question in that way.
Okay.
Yeah.
Could you
I would have
explain how
never
you
gotten
got 0.38 again then? Because I don't understand. Because when I did it, like thinking about it logically, I got 0.36.
Sure. Yeah, so there was, so when I'm calculating beta, I want to determine the proportion of times that I am accessing DRAM. Well, there's only two cases in which I access DRAM in this example. When I'm doing a page table walk and when I'm accessing DRAM. It already told me it's a single level page table, right? So I'm only going to do one, I'm only going to do one DRAM access when I do the page table access. And I'm only going to do one when I do the DRAM, obviously. So we need to consider both of these situations. So how often am I accessing the DRAM to do a page table walk? Well, I'm accessing the DRAM to do a page table walk every time that I get a cache miss. How many times do I get a cache miss? 20% of the time, right? So that's one case. And then how often am I going to DRAM to get the actual value? Well, I'm going to get it 90% of the time that I go to a page or table walk, right? So I have to account for this 0.2 as well, right? And so 0.2 times 0.9 gives me 0.18. I add those, and that's how I get 0.38.
Wouldn't wait, so 20% of the time you miss in the cache.
Mhm.
And
So this
then
is the same 0.2.
where does that 20% on 0.9 come from?
So I'm not always going to, like, I don't, for 90% of my accesses, I'm not going to the DRAM, right? I'm only going to the DRAM on 90% of my accesses if I have a cache miss, right? I only do a page, I can only
Yeah.
get like that 90%. That 90% only accounts for when I do the page table walk, right?
Oh, so it's the probability of a miss plus the probability that you hit DRAM, which is 0.18
exactly. So it's like,
individually.
it's a conditional probability,
Oh.
right?
Okay, that's yeah. So the way I looked at it was like I looked at it in a vacuum of like you have to access memory with 2 consecutive hits, which is 0.9 times 2
Mhm.
or 0.18 times 2, right? And then I just couldn't get the 0.02, which in their equation comes from the last term. But in this makes more sense. Okay.
Cool. As long as you understand it some way, then you don't need to worry. The others.
Wait, so quick thing. So the page table walk even getting there counts as DRAM, but like, so that.
Yeah, because we store the page tables in memory.
Oh, okay. So, like, what's the difference between like a page table and a specific thing called DRAM?
It just means that the data, like there's a difference, like the page table is kind of considered like metadata that helps us translate addresses, right? When we have the DRAM in this representation, we're just trying to show that the DRAM is like the actual data is stored in DRAM, which is why you
Like
see
your
like the
physical-
DRAM pointing to data. Yeah.
Oh, so that is your like kind of. So the page table is the metadata, like that represents
Mhm.
the like mappings, and the DRAM is actually where the pages are, or
Exactly.
So thank you.
Okay.